Row operations change the determinant of a matrix, but they change the determinant of a matrix in predictable ways. You don't have to memorize what you're looking at here. We're only going to take one message away from this. These are the things we do during Gauss-Jordan elimination, and they have the results of multiplying the determinant by a non-zero number, changing the sign of the determinant, and not changing the determinant at all. And the take-home message here is that if the determinant of A equals 0, then after Gauss-Jordan elimination, the determinant of the new matrix is still 0. 0 times k is 0, negative 0 is 0, and this doesn't change the determinant. So if you start with this determinant, you end up with this determinant. The determinant of the identity matrix I is 1. Why is that true? The identity matrix I is upper triangular. It has ones down the diagonal, and everything below the diagonal is 0. Of course, everything above the diagonal is 0 as well, but the important thing is that because it's upper triangular, its determinant is the product of its diagonal entries, and its diagonal entries are all 1. Ergo, if the determinant of A equals 0, then Gauss-Jordan elimination does not turn A to the identity matrix. Because if it did, we'd start with a determinant of 0 and wind up with a determinant of 1. And we know that doesn't happen. And then the invertible matrix theorem, if the determinant of A equals 0, A is not invertible. And in fact, this is an if and only if statement theorem. A is invertible if and only if the determinant of A is non-zero. Let's look at this in the 2x2 case. Because although I told you you didn't need to bother to memorize it, in the 2x2 case, we do have an explicit formula for the matrix inverse. In particular, A inverse is 1 divided by AD minus BC, and then times a matrix. You switch some entries, you add some diagonal signs, but for our purposes, this is what's important, because this AD minus BC, the product of the diagonal entries minus the product of the anti-diagonal entries, it's precisely the determinant of A. And this inverse exists if and only if we don't have a division by 0 error here. In this video, we've stated a major result, that a matrix is invertible if and only if its determinant is non-zero. As a numerical tool, this result has problems, but we'll use it to good effect as we move into the next chapter.